Eyes in the sky, gazing far.
Now before starting the chapter, we should know what is work. Work is defined as the dot product of force and displacement. We know the dot product of two vector quantities results to a scalar quantity. Now here force and displacement both are vector quantities. Hence the product result of these two vector quantities is a scalar quantity, that is work. So here W equals to Fs cos theta, where work is represented as W, F as force applied, and S as displacement, and the cosine of angle theta. Here the angle theta is the angle between the directions of force and displacement. This thing we have to keep in mind. Now for understanding the presence of angle theta, see this figure 4.1. Here the F acts on the object encircled with the point, that is the point of action of force. Now here as the force acts, the object is displaced with the position as marked on the next point, and the displacement is marked as S. So here the force acts and displacement occurs at an angle that is represented as theta. As you can see written, where theta is the angle between the force and displacement of the body. Now the force and displacement both are vector quantities, but their product work is a scalar quantity. So now keep in mind that the angle theta is the angle between the directions of force and displacement. This will help us to proceed to the other sections. Now we will discuss about some special cases of work, like positive work. Work is said to be positive when theta is greater than 0 and less than 90 degree, or pi by 2 in terms of radian, that is cos theta to be positive, hence work is positive. Now let me repeat, when force acts on an object and the displacement occurs at an angle, that angle is theta, which should be greater than 0 and less than 90 degree to make work positive. Next comes negative work, where work is said to be negative when the theta is equal to pi in terms of radians, which is equal to 180 degree. So we know that cosine of 180 degree is -1, that is negative. So work is also negative. Now comes no work, when the force acts in a direction at right angles to the direction or displacement, no work is done. Now for this, theta should be equal to pi by 2, that is 90 degree in terms of radians. For making work done equals to 0, cos 90 degree is only 0 for the degree values of cosine. Okay, so we will now talk about graphical interpretation of work. First one will be constant force. Now let us mark the assumptions. W for work, capital F for force applied, X for displacement. Now let's draw the graph. This is force versus displacement graph, where the y-axis will cover the force and x-axis will cover the displacement. Now as force is constant, so the slope of the graph will be just parallel to the x-axis. This is the x-axis. Now for this event, we will take two points at different timings, means we will select two displacements of different timings during this event. One is x1, another is x2. Let's take the constant force value as small f. So uh, this force applied is just represented for the y-axis direction, and the small f for the value of force. Now for this event, small f force for x1 displacement and small f force for x2 displacement. For both cases f is constant, so the value of f will be same for both timings. Now the occupied area of this force versus displacement graph will be will get us the value of work done. Now from the graph we get W equals to F whole into x1 minus x2 cos theta, which is equal to fx cos theta, where x is equals to x2 minus x1. Now as the force is constant, so for this problem the theta, this is the angle between the force and the displacement directions, will be equal to 0 degree. So cos 0 degrees value we know is 1. So the equation will result to W equals to Fx. Now this is the required equation of maximum work done applied by the force, which is constant. Now we will move on to the second part, that is variable force. Here we will proceed with the same assumptions. Now let's draw the graph. Same again, force versus displacement graph. Now here, as the force is variable, so the graph will be somewhat like this. Let's extend the x-axis. Now here the variable force displacement graph is shown in this figure. As you can see, here we will take a small strip of thickness ds, just a small strip of thickness ds. Okay, this is delta s, where s is displacement. Now let's join this with the slope of the graph. By this we will again get this, the area, which will represent the work done by the body. Now it has 4 points. Let's name them A, B, C and D. Now here the work done will be very small, as small strip of displacement is taken, so we will consider the work done as dW. Okay, so a small amount of work done is represented by the area ABCD. Therefore dW will be equal to area ABCD, that is AB into AD, AB into AD, length into breadth, which is equal to FDS. As we know, work is force into displacement, so here dW is equal to F into ds. Now here we are considering ABCD as triangle, that is we are considering this to be parallel to this is to be parallel to AB, as the amount of displacement is very small, as ds is so small that the area ABCD is taken as rectangle. Therefore W equals to integration of f ds, which is equal to the area below the curve. So here we are taking W as summation of FDS equal to area of the OPQ arc. Now here OPQ arc is just the slope of the variable force, as the under area is equal to the work done. So it can be concluded that the area occupied below the force displacement graph is represented by the amount of work done. It is to be noted that the area under the force displacement curve must be added with proper sign to obtain the work done by the force. Hello guys, my name is Rajdeep and this is my new channel, The Study Sukha. Do like, share and subscribe this channel. Students of first year diploma engineering may find this video very helpful, so as students of classes 11 and 12. And yes, do not forget to follow my Insta account Study Sukha.